Good morning, everyone. I am Teshnamgal, and today, on behalf of Team TASA, I would like to present about our AI-powered OrbitAR, and these are our members. So the purpose of creating this AI-powered OrbitAR is to create an interactive Android app that allows users to explore the solar system in AR using Vuforia with dynamic planet information powered by ChatGPT. The objective is to educate users about planets through an interactive AR experience combining 3D visualization, real-time rotation, and AI-driven contents. The target audience are students, educators, and space enthusiasts interested in interactive learning. And the platform on which we built this application is Unity, deployed on Android devices, leveraging Vuforia's AR and OpenAI's API for information retrieval. The background to create this app is due to the growing interest in space exploration and AR for education, and the core idea is to create a mobile application where users view a 3D solar system using Vuforia's image target, and users can interact with planet in two different modes. And the motivation to make this application is to make astronomy accessible and engaging through AR using AI to provide up-to-date, concise planet information without static data, leveraging Android's wide reach for broad accessibility. And the highlights for our project is immersive AR experience, where planets are visualized in 3D, orbiting the sun in the orbital scene with realistic rotations. Vuforia's image target tracking ensures planet appears in the real time, enhancing engagement. For interactive navigation, there are drop-down buttons which allow users to select and transition to any planet scene with a smooth fade to black effect. We have dynamic content with ChatGPT. Tapping on a planet fetches real-time information from OpenAI's API, which is then displayed in the UI text element. This eliminates the need for hard-coded data, ensuring fresh and concise information. And we have practical benefits, which are, first of all, educational value. It is ideal for school, teaching planetary science interactively. And for accessibility, it runs on Android, supporting a wide range of devices. And with scalability, it is easily extendable to include more celestial bodies or features. And for engagement, AR and AI makes learning fun, appealing to students and hobbyists. And the key highlight, which I am most proud of, is seamlessly integrating OpenAI's API to fetch dynamic planet information in real time, enhancing the app's educational value and interactivity. And now we'll be moving on with the demonstration.
So now I will do the project demonstrations. So firstly, if you focus on the solar system picture in the app, you will see a 3D model of the solar system. And the planets are rotating around the sun, and also they're spinning on their own axis. And if you tap on Saturn, it shows the information about the planet. And also, if we tap on Jupiter or Earth, whatever planet you want to tap on, and same thing, the detail will be pop up. And there has another feature too. In the top right corner, you can select any planet to view it more closely and to see its information. So that's the end of our project demonstrations. So for my part, I mainly focus on planet rotations with this code, and I make planets spin automatically by rotating it around y-axis every frame and using transform.rotate. So to make it look realistic, I also take the planet with a set angle, like Earth is 23.44 degree, using the Euler. And this stimulate how real planets spin in space, and while the script also include a tag feature to get the planet info from ChatGPT. So the main part I work on is making the rotation smooth, constant, and visually accurate for the AR experience. So that's all my part, and my friend will continue our presentations.
Now I'm going to be talking about my contributions to this project. First of all, which is orbital script for planetary control. The script controls the rotation of the planet around the sun, contributing to a realistic solar system visualization within the AR scene. It uses Unity's rotate around method to simulate smooth circular orbits in the XY plane. The speed of the planet's orbit is determined by a configurable orbital period, allowing each planet to have a unique and scientifically accurate rotation speed, such as Mercury orbiting faster and Jupiter slower. This setup is scalable and adjustable with the Unity's inspector, enabling consistent behavior across all planets and enhancing the educational realism of the experience. And my second contribution is ChatGPT's API integration into our project. The script enhances the educational value of the AR Solar System app by dynamically fetching concise planet information when the user taps on the planet. This is implemented in a script attached to each planet game object and uses fields such as planet name, API key, and info text. In the update method, the script detects users' taps on the screen and performs a physics raycast with the AR camera to determine whether the planet's sphere collider was tapped or not. And if so, it triggers a post request to OpenAI's endpoint using the GPT 3.5 turbo model. The JSON response is parsed using Newtonsoft.json to extract the content, which is then displayed in the info text. The script also includes robust error handling. It checks for missing fields and handles HTTP errors such as unauthorized access or timeout with clear feedback in the UI. A can tap Boolean flag and 2-second cooldowns are used to prevent rapid and repeated API calls. That is all for my contribution.
My part of the project focused on improving the user interaction by resetting or hiding the information test UI when the user tests anywhere in the background. So this helps avoid UI clutters and make the experience cleaner. In the script, I use Unity raycasting system to detect if the tab hits nothing, meaning the user tapped the background. If so, the UI test resets to a default instruction message, helping guide the user without showing outdated info. Next slide. So in this slide, this is the visual effect of my feature. So on the left, you can see the test UI displaying information about a celestial body after it has been tapped by the user. On the right, you see what happened after the user tapped on the empty background. This test reset to the default instruction message. This is important because it keeps the interface clean and avoid confusion, especially in AR and AR or VR, where too much on-screen text can overwhelm users. It's a simple but user-friendly interaction that helps maintain focus and provides ongoing guidance without clutter.
My name is C. In this presentation, I'm going to walk you through how the page transition works in this application. As we can see in the first slide, user will see a close-up view of the Jupiter, allowing them to explore a specific detail. When the back button is pressed, the scene transitions from this close-up view to an orbital perspective. This transition works by zooming out, giving the user a broader view of the Jupiter and its position within the solar system. This should help user to see a Jupiter in a wider context, making the experience more engaging. Moving on to the next slide. In this slide, let's talk about how the transition is controlled in the script. The script listens for the Android back button by detecting input.key.escape. Once this escape button is pressed, it begins a fade animation, gradually increasing the alpha of a user interface image from 0 transparent to the 1 fully black. This process creates a smooth transition effect that we see. After the fade, the script uses SyncManager.log syncs to switch to the orbital syncs. This approach ensures a similar visual chain, making the transition from the planet view to the orbital view smooth and neutral for the user.
Hello, James. So I'm Sakai Jong, and in our AI solar system project, I work on the same controller that manage how users switch between the planet. And so this is the main interactive user can explore planet in AI using Unity and the Lateria. So at the bottom there is a drop-down list. So when a user select a planet, their user fade out, the screen fade out and load a new scene. So this smooth transition here create a better user experience UX. So in next, we here we show what happens when the user turn on the Satan planet. This planet respond by showing information. So making is feel like real interactive project and so object. So this is more impressive learning experience. So this is not just 3D and model anymore. It is something the user can interact with. And so, so in the last slide, so this slide show RB tag for the space view, and no matter which planet that use a tag equal the same way. So this consistent behavior make the whole experience feel complete and our RB well designed. So I had some difficult and challenge I faced during the project. So I faced for getting the same transition to work with the frame animation, and I saw is by testing small parts of the logic, fixing them step by step, and so which helped me better understanding the Unity UI system. So that's all our presentation and demonstration. So thank you so much for listening. Thank you.